There are many thousands of objects orbiting the Earth that pose a real threat to space assets. Space Situational Awareness, or SSA, provides the ability to detect and track these space objects to reduce the risk of space asset destruction by implementing collision avoidance techniques. The aim for the 2020 Space Optical Fence System is to provide low-cost access to SSA capabilities to detect and characterize geostationary satellites. This will be completed with the following 4 objectives. 1. Improve timing system uncertainties. 2. Analyze and quantify system biases. 3. Conduct orbit determination on geostationary satellites. And 4. Light curve generation for informative characterization. Our system is a ground-based SSA sensor system that utilizes 4 DSLR cameras and a single board computer to reduce its cost compared to a telescope system.
The first step in achieving SSA is to acquire photometric data in the form of 30-second exposure photos. This allows us to separate stars, which appear as streaks, from geostationary satellites, which appear as blobs. Photometric data gives us the location of stars and satellites relative to the pixel coordinates of the photo, and time data is used to correlate the position to an inertial reference frame. Time data is created from a single board computer that is accurate to within 400 nanoseconds either side of UTC time. The single board computer operates an optocoupler relay board that triggers the cameras with a total delay of 2.6 microseconds. The next step is to process the photos. We create tracklets, which are a library for a set of detections that belong to the same satellite. These tracklets hold all the required information for computing their orbits and the light curves.
The next step is to quantify and account for the system's biases. We compare our tracklets against an official catalogue of satellite positions and assess and characterize any systematic errors. It was determined that the system produces angular detections accurate to 0.04 degrees. After this, the next step is to conduct orbit determination. Using a least squares regression approach, an orbital state curve is fitted that best describes a sequence of detections within the tracklet set. The produced orbit determination results coincided with catalogue data. From these results, the satellite's trajectory is predicted using the SGP4 propagation model, which accounts for perturbations due to the third body effects from the Sun and the Moon, and also perturbations caused by the oblateness of the Earth.
The final objective is to generate light curves. Light curves are datasets describing the light emitted or reflected by an object with respect to time or phase angle. By comparing light curves of the same object over multiple nights, we can identify satellites independently of the catalogue data. Future work for the Space Optical Fence System includes full satellite characterizations by correlating features of light curves to satellite-specific physical features, and improving automation by enhancing the system's real-time capabilities.